Let's get this going. Welcome to everybody. I'm glad to have you on board for this. As Maria has indicated, what we are endeavoring to do is to put together a series of presentations of the materials that have come from our book. Um, the first portion of the actual chapters are what is going to come today, which is really more the technical background. It's not the dealing with the application side. And there, as Maria said, there are three chapters to this, with different components being stressed in that. In subsequent sessions that we're going to have in the future, each one will be devoted to a particular application. So it's probably a bit sexier than the actual background materials because it's actually dealing with true applications. But for those of you that are, say, research students, either master's or PhD, the material that you're going to hear and on all of the applications are eminently usable anywhere that you've got, well, anywhere, most places in which you will have data and or models. So it will be or should be very beneficial for you if you're doing or conducting research studies with data. So that's kind of the um, sort of standing that we'd like to kind of throw out is this isn't just theoretical. This is very useful, and it's something that you can use immediately. So presenting today is going to be Professor Dr. Maria Kozlova. She is an associate professor at LUT University in Lappeenranta, Finland. She's been a colleague of mine now for 5 or so years, and today she will provide the background for SIMDEC and our SIMDEC book, and hopefully it will unveil numerous epiphanies that you will be able to use in your efforts. So please take it away, Maria.
Wow, thank you, Julian, for your kind words and excellent introduction to this initiative that we are doing. Yes, and Julian has been my opponent or examiner on my doctoral defense. It's how we met and how the whole SIMDEC story has started. And since then, yes, we are having very intense collaboration, and you'll see also Julian's name here in every single chapter and the book itself. And it's honestly been so much pleasure to do it together. So yes, let's jump into it. Chapter number 1, methodological landscape of sensitivity analysis and the place of SIMDEC. Yes, there are already some good reviews on sensitivity analysis methods, but we took a bit different angle here. Actually, should I say first that sensitivity analysis is the field that we identified the place of SIMDEC in, but actually now it's already expanding and we are looking more in empirical data application in machine learning and everything. But it's the future, and the current state is the book, and that's a sensitivity analysis, which is analysis of computational models. Okay. Further. Yes, so what different perspective did we take in this chapter? We actually looked at the sensitivity analysis as a process from where we start, which variables to take for the analysis, to the very end, how to use this analysis. And we tried to map the existing methodologies here and SIMDEC, and also to demonstrate its value with that. So first of all, I always thought of sensitivity analysis as something as simple as one at a time sensitivity analysis with just spider chart. We'll see a picture of it. And I've never I've never could have imagined that there is such a big field until I met it actually. And there, one important phase of the analysis before the data analysis can even start is the data generation. And again, if you're working with empirical data, then this part is already taken care of. You already have a ready data set. But for computational models, you need to first generate that data set. And there you will take many different nuances into account, starting from what's the focus of your analysis, which defines which kind of variables you would take. And the most common probably way of doing things there is to study system behavior to understand how everything works inside. And then you take those inputs that actually characterize the system behavior and affect the model output, or at least potentially affect it. Then you could study model fidelity. So whether design of the model, parameters of the model affect its performance. And then you can also, that's already a bit weird application, but still you can also check the sensitivity of your sensitivity analysis method to see if your conclusions would change if you adopt different methods or different visualization. Then when you decided the set of variables, you proceed to the variation or uncertainty modeling in your model. And there are numerous approaches there. And one of the most advised is to use actually fitted empirical distribution. So you take historical data, right, to make your model the most realistic. You fit the distribution to it. You properly model for correlations, dependencies in your model to make it as realistic as possible. However, in our book, we also saw that in many cases, it's very hard to find any historical data or to even refer to it at all if we are talking about some new phenomena. And in those cases, plus there are a lot of decision variables that can be modeled. So it's like, what kind of history are we talking about if it's under our control to choose one or another pathway? So uniform distributions has proven to be working quite nicely in many applications and providing good insight into system behavior. Then there are different sampling strategies. So when the distribution is defined, usually what if you're using Excel or some basic random function, then it's a simple random sampling. But there are actually quite a lot of science going on around it because simple random sampling fills the space not very uniformly, and that affects the precision of the estimates. And by estimates, I mean sensitivity indices. And here, quasi-random sampling or quasi-Monte Carlo has been recommended over all other techniques. And again, we did a few experiments here and there, and it appeared to be that with SIMDEC, it's actually not as critical to go beyond simple random sampling because it's not about any more precision of sensitivity indices. It's about the shape of the effects. So even if sensitivity indices can be plus minus some error, variation, or confidence interval, then you anyway visualize those effects on the SIMDEC visualization, and there it doesn't matter really what sampling techniques you were using. It just shows you the shape of those effects, which remains unchanged. And now we are moving to the next big phase, which is actual data analysis. Here, what can we say? There are books written about it. For computing sensitivity indices or for quantitative analysis of your data set. It's mostly the field responsible called global sensitivity analysis, and there are numerous of methods in there. But something that we developed here for SIMDEC called simple binning approach, which is implementation of Sobol indices or variance-based sensitivity indices. It proven to be for us the most convenient because it's computationally light, because it's intuitively simple, and you can easily explain it to practitioners. What does it do? Because it takes into account correlations or dependencies, so you can also easily use it with empirical data, no matter how intricate the dependencies there are. And yes, it works with a given data. So many other techniques require the access to the model to produce different sets of simulations. And this one doesn't need to. It just, you have input output data, and that's it. You can just compute indices based on that. And the final stage is visualization. An interesting thing that we noticed in global sensitivity analysis field is that it often stops at the moment of computing sensitivity indices, and nobody visualizes anything. Sometimes scatter plots are used, sometimes probability distributions, histograms, but neither say much, and they have all restrictions on how many, in terms of multidimensionality. So it's very hard to show actually like high-level interactions or shape of effects with multiple variables affecting the output. Same goes with heat maps, response surfaces. Parallel coordinate plots are a good step towards multidimensional visualization, but they're often messy and it requires quite a lot of tweaking before you can extract the visual insight from there. So it hasn't been adopted widely. Yes, and here where SIMDEC comes, and actually wants what we want is actually to make it a standard visualization applied to any sensitivity analysis study. Why? Because it actually shows the multidimensional effect, because it shows the interactions. Yeah, and it can also work with differently shaped data. If your output is not that visible on a histogram, which is the basic SIMDEC, then you can use box plots as well. So, and there you'll see all the effects of your model or data. So that's about the overview that we have done there. Julian, you wanted to say something?
Yeah, let me just ask you a question.
Yes, go ahead.
Why would you use, so in that column 4, why use sensitivity indices to evaluate effects when instead of, say, statistics and p-values? So why not standard
Yeah,
statistical tests?
good.
Given that we've got some grad students here.
Yeah, good question. My personal understanding of how it all was developing is that statistics was normally applied to empirical data, and then when something like scientific experiments evolved, there was a field of design of experiments that would adapt the statistics to the nature of those experiments. And then when it evolved into digital experiments or simulations, then the field made another big step, and departing from classical statistics into global sensitivity analysis. So yeah, because, well, simulations are a bit different also, because for example, we for sure know that we explain the entire variance of the output if we account for all the uncertainties in the model or variations in the model. It's never the case with empirical data, right? So it's like,
Okay. So let me, I'm just sort of more background stuff. It might be helpful to kind of explain the difference between one-at-a-time sensitivity analysis and global sensitivity analysis? I mean, it's all sensitivity analysis, isn't it?
That's true. That's true. And yes, one-at-a-time sensitivity analysis. I was thinking that's the only sensitivity analysis that exists for a long time. One-at-a-time sensitivity analysis is not a quantitative metric. You don't have an index or a value showing how different inputs are important. That's one thing. Another thing, it's a local approach. So you vary only around the base point, right? Plus minus every factor. And then the last thing is that one at a time, the name of it actually is the most limiting thing, because you miss so much variation in there. Like imagine you have not additive model, but at least simple multiplication in your model, and one at a time already would fail dramatically to capture the entire extent of how different your output values can go. Whereas global sensitivity analysis, it's global, it explores the entire space, so it will get you the extreme values as well. But for many people, it's not comfortable to look at the extreme values of your model. So that was one of the arguments why global sensitivity analysis is not adopted that widely.
If I could just reinforce that a bit more, if you didn't hear Andrea Saltelli's talk a couple of weeks ago, and he's given multiple talks in his life, obviously, he has this figure which shows you. I mean, as Maria says, when I heard of sensitivity analysis, in my mind, it was always, oh, let's just change this value and see what the impact is, and then we'll change this value again and see what the impact is, which is, I think, how 99% of the people view sensitivity analysis. The problem with it is that it basically will miss massive portions of the solution space. And if you've got numbers of variables which have dependencies upon each other and interact with each other, Andrea has this slide which shows if you've got two variables, you'll miss about 25% of the solution space. If you've got three variables, you miss about 50%. And if you've got 10 variables, you miss 99.75% of the solution space. So if you're doing one-at-a-time sensitivity analysis with many variables, or even, just a few variables, you will miss massive portions of the analysis. And so you need to have global sensitivity analysis where you vary all of the parameters simultaneously in order to capture the impacts that are taking place within either your model or within your data. So I just wanted to frame that for our grad students here. If you're going to do sensitivity analysis, it really has to be global sensitivity analysis. Otherwise, you're almost better off doing nothing. And doing nothing is not really an approach. So that's kind of why we're doing it.
And if you do global sensitivity analysis, again, what we argue here is that computing sensitivity indices alone, even though they are global, is not enough to understand how your model behaves. It answers the question which inputs are important and how much, but it doesn't answer you the question how exactly they interactively affect the output, what is the shape of that influence that they have. So it really worth looking into visualization of that, and that's where Simdeck comes into play and helps you understand what exactly is the shape of those interactions and effects in your model. Yep. Thank you, Julian. How do I get further? Oh, I got stuck. Yes, got unstuck. Here. So yeah, there are different visualizations that are often used independently from global sensitivity analysis. And the first two are actually one-at-a-time sensitivity analysis, spider chart and tornado diagram. Again, it's exactly everything what Julian said. you're not exploring the space here. And even your output axis, which is y-axis on the spider chart and x-axis on the tornado diagram, it would have so much fewer range of variation compared to if you made all those factors to be negative or positive, assuming the model is linear. Then scatterplot is also a good way to, scatterplot is a good way to see the shape of the dependency from input to output, but it's not that multidimensional. You can introduce colors, shapes, and some other things, but it's very quickly gets really messy and hard to read. And then nobody usually go that extent anyway. But scatterplot can be already considered as a kind of global way or visualizing global data. Then histogram D here, it's an excellent step forward to see the entire space of the output, right, in the global methods. But the problem is that you cannot see much more than that. You see the global minimum, the global maximum, and the shape of the distribution. You can compute a bunch of statistics out of that, and that's it. You don't know how it's connected to the inputs at all. Heat map is the idea of going forward with multidimensionality and portraying the output here as a color scheme and the influence of two inputs on that output. But again, we are limited to inputs, and the shape of the output is perceived a bit not that intuitively. Surface plot, response surface is just another way. It's just 3D heat map, but it has the same dimensionality problem. And then parallel coordinate plot is something that actually has the potential to show the links between all the inputs and the outputs. But again, when you have thousands of data points, it gets super, super messy. And then little people actually go to, a few people go to the extent of combining it with global sensitivity analysis to actually filter out the non-important inputs and show only those who affect the output the most. And then you still have this problem that the output is just one line, and you can have maximum two inputs around it, and it's already tricky how you're going to visualize the effects. Yep. So all these problems with global sensitivity analysis and with sensitivity analysis even in general lead to very low adoption rates of it. So we did a very simple exercise. We did some keyword search in Scopus, and we checked all the papers which has a keyword model in it, and there are a few millions. And of course, it's not clean analysis or precise because there's a bunch of papers that don't do any quantitative exercise even there. But anyway, we believe that it's sufficiently representative. And yes, what we found is that only 1% of papers use any kind of sensitivity analysis, and most of it is actually one at a time. And global sensitivity analysis is only a minor share of it. So it's not, although it's very cool science and it has a lot of publications and books, etc., it's not very much out there. Julian?
Why is that?
Yes, all those things. First of all, I would argue that number one reason is that sensitivity indices alone is not enough. I mean, they show you how different inputs, they allow you to rank inputs in terms of their importance, and that's it. It's too little of a function for an extent that you need to go over in order to grasp different methodologies, how they mathematically work, etc., etc. So it's like learning another course of demanding and difficult statistics. Then if statistics is commonly taught at universities, global sensitivity analysis is not. So that's another big problem. And so it often happened that the schools that are accustomed to using global sensitivity analysis, they keep teaching their PhD student to use it, but that's it. Doesn't spread that much further, unfortunately. Yes, and again, with SIMDEC, we want to change this.
Why not just use, I mean, why use SIMDEC? Why not use Shapley values or Sobol indices?
But that's a simple question. It was actually in the first slide. Because all the Shapley values, Sobol indices, and all other methods there usually stop at computing the values of indices or the values for importance of different variables. It's the SIMDEC that actually uses sensitivity indices as just an instrument to produce a meaningful visualization. So, and it's visualization that really creates understanding how model behaves.
Could you, instead of using binning though, could you use Shapley values or Sobol indices and then do the
Yes,
vision?
yes.
Why wouldn't we
I,
just do?
can I be a bit silly here? Because it was easier to create something own than to understand how all those complicated things work. But no, again, there are a few limitations of those methods. We wanted something that works with the given data, and we wanted something that works with correlations, and we wanted something that works with the relatively small computational expenses. So because it's not the target of the analysis to compute those indices, it's just a step in the algorithm which we need to produce meaningful visualization. We needed it fast and it in all the kind of data set that it would be given. That's it.
Yeah, I think the key part there is it's much faster using
Yeah.
the bin and uses a lot less data, and
Yes.
and the results are, let's say, at least as good.
Yeah, the results are sufficient. The results are sufficient. So, and they're comparable. We again ran a few experiments, and at least with original Sobol indices that require much more computations, we are we're getting away with a good precision and with much smaller data sets and much faster. So why not then? Okay, so we were talking about the adoption of sensitivity analysis, and we actually broke it down a bit by subject area. You can see here where sensitivity analysis is more or less popular and where global sensitivity analysis is adopted a bit more. But again, all these percentage points are so ridiculously small that it's sad. And then we also checked some few particular keywords, some modeling traditions, let's say, at schools or applications. And again, we see pretty much the same picture that global sensitivity analysis alone exists in way less than 1% of papers. And sensitivity analysis in general, whichever that is also quite a rare thing, which is very sad. It also shows something that Andrea Sautelli have been criticizing in terms of modeling and policy making, also in his Nature publication manifesto. The world is full into determinism, and they all want to have their precise value of emissions, of costs, of profitability, of efficiency, etc., etc. And then that precise value would be a threshold for making the decision. And it's often it's custom in many disciplines, and we need to break through that custom in order to make meaningful decision support or understanding the systems. Yes, but we'll get back to determinism actually. Conclusions from the chapter 1. Nor existing quantitative methods nor visualizations alone are sufficient for capturing complex model behavior. Hence, low adoption of global sensitivity analysis and even sensitivity analysis in general. And our intention is to change it, to revolutionize the analysis of computational model with a hybrid all-encompassing SIMDEC. And what the hell is SIMDEC? It's coming in chapter 2. So if you have, let's discuss if there are any comments, questions, and then we can switch to the next chapter.
Well, let me throw it out something to our, let's say, our grad students, or even our very senior researchers, I note here. If you've got a model, if you've got data, you really need to be doing a sensitivity analysis of it. And so, I mean, this is a major deficiency of, a surprisingly major deficiency of a lot of fields of research and even of data analysis, is that this is something that actually needs to be done, but it's not done. And so if you are, say, starting out and you're doing some sort of study, it's something you need to put into your analysis, which is deficient in the literature. So when you're doing your literature reviews and surveys and backgrounds of materials to support what you are doing, whatever application it is that you're working on, you will probably encounter what Maria has just shown you, is that 90 to 95% of all studies do nothing in terms of sensitivity analysis, and then even those that do it deficiently. So that provides you, or it can provide you, with support and justification for including that in whatever studies you're doing, to make it more appealing publication-wise. And that's one of those background necessities if you are to progress in, say, the academic world and academic publishing. So keep that in mind as you progress.
Yes, something to add here is actually in a lot of applications that we considered in this book, and it's actually coming in chapter 3. There was quite a few experiences where we would find an error, or where we would refine a model, having the results of sensitivity analysis. And it's very, very common that whenever you start shaking your model, analyzing how it behaves, you find something that is not consistent in there, or not aligned with your logic, and then you find somewhere a place where it's not behaving as it's supposed to. So it's very useful tool, not only for making an extra publication or understanding your model a bit better. It's also a very useful tool to actually building your model iteratively.